Okay, so hi everyone. So today we have Annalisa Pillepich for our Wednesday seminar, and I will give a brief introduction about Annalisa, and then I will give her the floor. So Annalisa studied at in Italy at the Università degli Studi di Pisa. And after that, she moved to Switzerland, where in 2010 she obtained a PhD in physics. Then, since the university, Annalisa has directed her attention toward the origin of the universe. And now that she's a permanent staff member at the Max Planck Institute for Astronomy in Heidelberg, she's leading a group on galaxies and cosmology theory, which is focused on modeling and understanding the formation and evolution of cosmic structures and galaxies in the context of the standard cosmological models and its plausible alternatives. And one last important thing to mention is that Annalisa just got awarded an ERC Consolidator grant, so congratulations to Annalisa, with a project called Cosmic Key, which I suppose she will talk a little bit about today. And without any further ado, now the floor is yours, Annalisa.
Thank you very much. Can you hear me well?
Yes, we can.
And you see my slides?
Yes.
Yeah. Okay, cool. Thank you very much. Good morning, everyone. Yeah, it's a pleasure to be with you. And today, so we're actually going to talk about the halting of star formation in galaxies, mostly massive galaxies. And we will start from a theoretical perspective, from a numerical and simulation perspective, as this movie is meant to suggest. Here you're seeing the formation and evolution of a galaxy that by redshift 0 will resemble Andromeda. In the center, you are seeing gas density. On the bottom right, you are seeing zoom-in views on this galaxy in stellar light composite, and again, gas column density. On the left is the large-scale structure around this object. Earlier on, it was in dark matter density, and now is again in gas. So this movie, that now we are rotating around the galaxy, and it will change color just to show you, instead of gas density, gas metallicity. So this movie is actually meant to remind us of three main things. Galaxies are not isolated. They can accrete smaller ones, as this guy that is coming in now and bouncing on the disk of the main object, and they can also merge into more massive ones. Second, galaxies can accrete gas. They can accrete the gas from satellites, from their circumgalactic halo, or directly from the large-scale structure. And finally, galaxies can get rid of their gas. As you may notice here, sometimes there are flows of gas coming out from the galaxies. And we think that these are triggered by energy injection from star-forming region and supermassive black holes at the center of galaxies. So gas flows and inflows and feedback are fundamental physical processes to understand quenching. So the big underlying question of my talk is what stops the formation of stars in massive galaxies? And in the past 15 to 20 years, people have come up with a number of possibilities. Nowadays, the most popular and the most accepted and possible scenario is feedback from supermassive black holes, from the supermassive black holes at the center of most massive galaxies that are active, or AGM. By feedback, we mean the transfer of energy, momentum, mass, and radiation from the supermassive black holes to the surroundings. However, other processes have also been proposed to stop star formation in galaxies, like for morphological quenching, galaxy-galaxy mergers, or gravitational heating. However, my work and this talk starts from the boundary condition that what drives the stopping of star formation in massive galaxies is feedback from supermassive black holes. And in particular, I will convey the idea that the gas around galaxies, and in particular the gas around normal L-star galaxies, encode enormous information content to prove or disprove this supermassive black hole feedback quenching mechanism. Or more generally, the main message of my talk is that whatever quenches star formation in galaxies is expected to leave quantitative and observable imprint in the physical properties of the gas in and around galaxies. I will support my claim by first giving you an overview of cosmological galaxy simulations, just to have everybody on the same page. I will give you more details on how the quenching is achieved and therefore postulated and suggested by state-of-the-art cosmological simulations of galaxies. I will then give you, I went backwards. I will then show you a number of predictions from this kind of simulations that really show the direct connection between supermassive black hole feedback and the physical state, thermodynamical ionization, kinematic state of the gaseous halo around galaxies. And I will finish with the cherry on the cake, which is actually a new phenomenon that we have discovered in actual galaxy data in the Slow and Digital Sky survey that we call anisotropic satellite quenching or angular conformity, and that really statistically exemplifies the link across all these elements of the galactic ecosystems depicted in this image. So for those of you who don't do this business, just to have everybody on the same page, I will use the words quenched, quiescent, quenching, or red galaxies as interchangeably, meaning galaxies that from a population perspective have halted star formation. We will talk about supermassive black holes as objects that can accrete gas from their surrounding and can transform some of this energy into feedback. And I'm thinking about objects above 10 to the 5, 10 to the 6 solar masses at the center of massive galaxies. And I will also use the words circumgalactic medium, intercluster medium, halo gas, gaseous halo, or galactic atmosphere, interchangeably again to simply denote all the gas, also the volume filling gas in and around galaxies within the gravitational potential wells of the dark matter halos in which galaxies form and evolve. So let's get started. The movie from the beginning is from a simulation we call TNG50. And TNG50 is a cosmological magnetohydrodynamical simulation of galaxies. What does this mean? It should be clear in the next few minutes. Now, the numerical community who works on galaxies has really been progressing on two parallel tracks. On the one hand, people simulate individual galaxies. This can be idealized and isolated, or they can be less idealized and in the full cosmological context, but still one simulation, one galaxy, as these two that I'm showing you here across about 30 kpc. What really sets apart these simulations is that they can reach very good spatial resolution of the order of the parsec level. And so they can also implement physical processes down to this level and also including many physical processes. On the other hand, since a handful of years, it has been possible to simulate galaxies in the full cosmological context across large-scale cosmological volumes. So these are the simulations that I will be talking about throughout the talk, so watch out if you are not familiar with them. In this kind of simulations, we follow the convolution of dark matter, usually called gas, stars, supermassive black holes, and in some cases magnetic fields, across tens or 100 megaparsec volumes, from the initial conditions of the universe, with statistical properties consistent with what we observe from the cosmic microwave background, all the way to redshift 0, where dark matter arranges itself in the cosmic web you can see here of filaments, sheets, voids, and halos. But gas, mostly hydrogen and helium, permeates everything. And in the scale of 1 pixel in this image, these kind of simulations also resolved galaxies. And with them, they also follow the highly non-linearly coupled phenomena that govern galaxy evolution. So we can model what happens within galaxies and their effects on the surrounding dark matter and gas in the halos and in the large scale structure, and vice versa. The evolution of these galaxies at the center of halos depends on the large scale structure. For example, we know that the evolution of halos and galaxies chiefly depends on the hierarchical growth of structure. How is this achieved? By solving numerically the coupled equations of gravity and magnetohydrodynamics, or simply hydrodynamics, in expanding universes, in turn coupled to formula, equations, and numerical representations of those phenomena that happened within galaxies. Star formation, microphysics as gas cooling and heating, stellar evolution, and their subsequent enrichment of the gas with metals, and the stellar feedback, and the seeding, growth, and feedback from supermassive black holes. All these phenomena are realized in a so-called subgrid fashion down to spatial scales of the order of, say, a kiloparsec, or at best 100 parsec or so on average in the simulation I mentioned earlier, TNG-15. So we're talking about spatial scales of giant molecular clouds and above in these kind of simulations. So these kinds of simulations are, for example, Illustris, Eagle, or Horizon AGN Magneticum that came out in 2014, 2015, or more recently, the next generation Illustris or SIMBA. These were all made by independent groups across the world with different underlying numerical codes and different underlying physical assumptions. And so, for example, in these simulations, star formation occurs in gas above a certain density. And stellar particles represent mono-age stellar populations of 10 to the 4, 10 to the 5, or even 10 to the 6 solar masses of stars. Now, I'm going to talk to you about a bit more about Illustris TNG, which is the next generation Illustris project that I have co-led and developed with my colleagues across Germany and the United States. This is a series of cosmological magnetohydrodynamical simulations of galaxies where we aim to model the coevolution of thousands of objects across 13.8 billion years of cosmic evolution. Our flagship runs are depicted in the center. We call them TNG-100, TNG-300, TNG-50. Larger volumes allow us to have more statistics in terms of galaxies and more statistics on the most massive halos. Smaller volume allows us better resolution. These are all made with the underlying code AREPO, which is fabulous. They include magnetic fields. They're all based on the complex model for galaxy formation, which we call the Illustris TNG model. I will give you some more details in a moment, and more details are here for later reference. The TNG simulations remain an unmatched combination of volume and resolution nowadays, and their output, we made it fully public, and it has been used in more than 500 scientific publications from the community. How is that possible? Models like Illustris TNG have enormous information content. This makes them highly testable and widely applicable across many domains of astrophysics, whether you are interested in the phase-space properties of colder matter or of the stars and star formation, or whether you care about the many different manifestations of gas across cosmic scales. Importantly, these simulations also produce output that are reasonably realistic across many instances. Here I show you, for example, just a few of the galaxies that we can sample and realize in these large cosmological volumes in stellar-like composite. However, we do not only simulate a few galaxies, but thousands of them, and across wavelength. For example, these are galaxies, Redshift 2 from TNG-50, Fezon and John. They are star forming. I chose them to be thin, and you see them in age alpha light and in stellar light in a composite on the right. As I mentioned earlier, the majority of the galaxies are not isolated. In fact, the majority of them live in groups and clusters of galaxies. Like these two objects, these are groups, these are Virgo mass groups or clusters of galaxies. You can see individual galaxies here depicted in mass, stellar mass density projected. All this is possible because, as I said, in these simulations, we follow the evolution of matter components across large scales, like the large-scale structure. You're seeing here a large-scale structure, but maybe you have never seen it in this form. This is the mass-weighted Mach numbers of cosmic shocks, where you can see shocks due to the gravitational collapse that form filaments, as well as shocks driven by feedback from the innermost regions of galaxies. And indeed, the strength of this simulation is that, compared to other models, like semi-analytical models or others, is that they really allow us to understand and study the spatially resolved gas across many phases. Here you're seeing, for example, pressure waves of the gas at the core of a Virgo mass cluster. But we can also say in the same simulation, we can also see small cold gas clouds depicted here in otherwise hot 10 to the 7 Kelvin halos around so-called LRGs, luminous red galaxies. And we can also study feedback from satellite galaxies as they fall and orbit into more massive ones, and as they are going through strong ramp pressure stripping of their gas. So the outcome of these simulations are not just quite beautiful, but they're also reasonably realistic, and this makes them more useful. I'm going to mention 3 points that are relevant for the topic of this talk. Firstly, simulations like TNG return approximately the evolution of the cosmic star formation rate density. Maybe you guys know what they're talking about is the average star formation across all galaxies in the world, and we know that it peaks according to both simulations as observations around redshift 2 and 3, and then it declines. Whereas this is partially by construction in our models, it's not by construction that realism number 2, simulations like TNG predicts and return as observed the existence of a star-forming main sequence also at high redshift. Here, one dot is one galaxy. It's plotted the global integrated star formation rate in the galaxies as a function of galaxy stellar mass. And you can see that in the simulations, galaxies typically form a sequence whereby the more massive the galaxy, the higher the star formation rates. And higher the redshift, the higher is the locus of the star-forming main sequence. But you can also see that simulations like TNG also show galaxies that fall off from the main sequence, so they are less star-forming. In fact, point of realism number 3, it has only been since a few years that simulations of this time can return realistically to distinct classes of galaxies, blue and red. This is a number density distribution of galaxies in the G-R color versus stellar mass plane. In black is observations. In blue is our simulations, where you can see that according to, there is a blue cloud and a red sequence, and according to both observations and simulations, below 10 to the 10 solar masses in stars, galaxies are mostly blue. Above 10 to the 11 solar masses in stars, galaxies are mostly red. And these simulations also naturally return the second order relationships between star formation status and other morphological structural properties. For example, blue star forming galaxies are realized in the simulation as disky and spirally, as observed, and red quiescent galaxies are typically a cocoon distribution, featureless cocoon distribution of stellar light. This is based on color. We could show the same in SFR, and we can also show it in terms of the number of fraction of galaxies that are quenched as a function of galaxy stellar mass. The colors are simulations, the observations are in gray. And again, both observations and new simulations agree that below 10 to the 10 solar masses, galaxies are mostly star forming, and above 10 to the 11 solar masses, galaxies are mostly quenched in the world. And you can see the comparison across 2 different models. The new simulations illustrate TNG, and the previous simulation of my team illustrates, and these differences are due to different implementations of AGN feedback. But the one thing that I really want you to notice here is that at the mass scales where Milky Way and Andromeda live, that I'm gonna call it transitional in stellar masses between 10 to the 10.5 and 10 to the 11, the galaxies can be both quenched and start forming in similar frequencies. And so at the transitional mass scale, the quenching mechanism must be common, not just in clusters, not just in massive galaxies. And in this transitional mass regime, feedback from stars and feedback from supermassive black holes are thought to be simultaneously occurring and important. And this is why we will focus on this regime in the remainder of the talk. So, equipped with this simulation that are reasonably realistic, over the past years as a community and in my team, we have provided insights about how star formation progresses in galaxies across the mass scales and across times, and how star formation declines. I'm going to give you again an overview for those of you who are not thinking about star formation in galaxy every day. As I showed you in the plot earlier, the star formation activity of galaxies depends on their mass, and this is true from both simulations and observations. In fact, both observations and simulations agree that the star formation status of galaxies depends also on their environment. At fixed galaxy stellar mass, the star formation rates of galaxies that are isolated is higher observationally than in galaxies that are not isolated, that are in higher density environments. In a lambda CDM cosmological scenario, and so from a theoretical perspective, this is related to the underlying location in their matter halos and on whether satellite, to the underlying their matter halo mass, and on whether galaxies are central of their halo or are satellite of a more massive halos dominated by another more massive galaxy. Again, more generally still, the star formation activity of galaxies have been recognized to depend on the interplay between internal and environmental processes. And observations, simulations and most observations agree that to zeroth order, whether a galaxy start forming or quenched depends on its availability of cold gas. And it makes sense, right, guys? Because star formation depends on cold gas. And if you don't have the fuel for star formation, you don't make stars. But so galaxies that are quenched are possibly galaxies that have undergone some kind of cold gas loss or cold gas removal, or that have been impeded to have their gas cooling. From the simulation perspective, the kind that I talked to you about, two are the chief mechanisms that produce quenching. At the internal level, supermassive black hole feedback. At the environmental level, gas stripping. I'm going to give you a few details on both and then move on to the gaseous halos. So let's start with supermassive black hole feedback. Again, if you're not of this field, this is one of the most important messages of the last 10 years. According to simulations, no mechanism other than feedback from supermassive black holes have been shown to be able to quench an entire population of simulated massive galaxies to the levels that are consistent with observations. And this is why my boundary condition of supermassive black hole driven feedback doing quenching, because yes, mergers may quench galaxies, but maybe temporarily, and not for all the galaxies populations as observed. Morphological quenching may quench galaxies also sometimes, and if you have already removed some gas. But here we need a general purpose mechanism. And in our simulations that also include some level of morphological quenching and mergers, this is supermassive black hole feedback. I'm going to prove this with this plot. This is again galaxy color versus galaxy stellar mass. And in red, you see the galaxies realized with the elastic TNG model. Now, let's assume that we run this simulation without feedback from supermassive black holes. What you get are the same galaxies in the same volume, but with different colors. These are the blue ones. So in the TNG model, a red quiescent population of high mass galaxies develop only when the AGN feedback is on, when the supermassive black holes are doing their job. And in particular in our model, this is happening when supermassive black hole feedback is in its low accretion rate, radiatively inefficient kinetic mode. I'm going to give you some details about the implementation of supermassive black hole feedback in our simulations. So on top of star formations, gas cooling and heating, and feedback from stars, we implement supermassive black hole feedback. And the idea is that we don't know how supermassive black holes form. We put them in galaxies at a certain point earlier on in time. We allow them to grow, and by accreting gas and by mergers. This energy can be converted into feedback. And in our simulations, we postulate 3 channels of feedback from supermassive black holes. Channel number 1. If the black holes is accreting at high Eddington ratios, the black holes donates thermal mode to the surrounding gas in a continuous thermal dump, which we call thermal or quasar mode. If the black holes are accreting at low Eddington ratios, percentage level or below, the idea is that the black hole thinking about coronal winds and their larger scale manifestation, imparts momentum to the gas surrounding the black hole in a pulsated manner in different direction at different time steps of the black hole, so that as averaging time, this is a isotropic energy injection, but kinetic. And finally, at all times, we also modulate the cooling of the gas, or the cooling functions of the gas around the black holes, because of the radiation emitted by the black holes. So this is what we implement at the injection scale, at the subgrid level, you know, at the level of these cells that you see here. This is the Voronoi tessellation of our code of the gas. And this is what happens when you actually implement this model, run the simulations, and see what happens. So in massive galaxies in the model, the kinetic mode feedback is the predominant one, and is the one that quenches star formation. You can see how it acts here. This is a galaxy, actually a redshift 1, before quenching, and as it has undergone for the first time kinetic feedback. You are seeing it at dawn, and you're seeing gas velocity, density, temperature, density, metallicity from left to right. So supermassive black hole driven wind drives large scale outflows of thousands of kilometers a second. That shock hits the gas also at large distances from the galaxies. These are tens of kiloparsec, creating cocoon of overpressurized underdense gas, which is highly polluted. So in our models, the supermassive black hole feedback triggers the quenching of star formation because it removes the core gas from the center. It offsets the cooling time of the gas at various distances from the galaxy. So this gas cannot cool in the future to give more star formation. But also what I want you to notice is that the effects of supermassive black holes can be seen, at least according to the simulations, at very large distances, orders of magnitude larger than wherever are the energy injection of this energy of this phenomena at the black hole level. And the effects are certainly not isotropic, as you can see here. Good. What about low mass galaxies? Galaxies below 10 to the 10 solar masses. Again, if you're not thinking about this all the time, let me remind you that galaxies which are low mass are typically star forming, unless they are satellites. This is, again, quench fraction of galaxies versus galaxy stellar mass. In gray are observations, in black are our simulations, good agreement. They both agree that if galaxies are on their own, are isolated and centrals, at the low mass end, they are rarely quenched. However, if they happen to be in more massive halos of 10 to the 13, 10 to the 14, 10 to the 15 solar masses, the probability that these are quenched skyrockets. In fact, in 10 to the 15 solar masses, the majority of galaxies are quenched. Okay? And this is also associated to many other properties of satellite galaxies versus isolated ones. So what is the cause? Again, according to simulation, the most obvious mechanism that affects the star formation status of galaxies is the removal of the core gas from these galaxies. And this removal is mostly done, according to simulation, by round pressure stripping. As satellite galaxies orbit in more massive hosts, they undergo many physical processes. One of them is round pressure stripping that produces jellyfish galaxies. These have been observed in various wavelengths, and we can simulate them. These are emergent phenomena in the simulations. In fact, we have placed 80,000 images of our simulated galaxies in the universe, and now we have many thousands of jellyfish galaxies visually inspected by citizen science, and we are scientists, and we actually my team has worked a lot on galaxy evolution in dense environments. However, I'm going to stop here for these purposes, and I just wanted to give you the overview. Let's go back to massive galaxies. As I said, according to TNG, these kinetic energy injections vacate the gas from the central region of galaxy, and actually also from the halos around galaxies. This gas ejection as quenching mechanism and driven by supermassive black hole feedback is not just something postulated by TNG, but it's something that comes out in all galaxy simulations. You can see here that, however, different simulations and different models predict different quantitative predictions on terms of the amount of gas that is remaining within halos around galaxies. This is gas fraction to total mass within halos as a function of halo mass. The two plots are very similar. I just wanted to show them both. And so different simulations agree qualitatively that some gas has to be removed from the gaseous, from the Darmstadt halos, but they disagree on how much of it shall be removed from galaxies and gaseous halos. Why this disagreement? Well, because current cosmological galaxy simulations have been mostly designed and to reproduce mostly properties of galaxies that refer to their stellar content. And they've been validated mostly so far against stellar quantities. Why is that? Because observations about the stellar content of galaxies are the ones that have been the best over the last 20 years and the most numerous. However, as I mentioned earlier, and as this movie shows clearly, gas inflows and outflows and feedback leave their most direct impact on the gas in galaxies and around galaxies, not on the stars. And so this is where we can go and look for a stronger constraint on the functioning of feedback models that in turn may be the responsible physical causes for the quenching of star formation. And so in the main part and second part of my talk, I will then give you details on how these simulations predict testable effects of feedback on the surrounding gas in the circumgalactic medium. And we will focus on this transitional mass regime of 10 to the 10 to 10 to the 11 solar masses, the one of the Milky Way, where galaxies may be at the same time start forming and quiescing, different galaxies, or even same galaxies. We will contrast sometimes start forming and quiescing galaxies. And why? Because quiescent galaxies, according to our models, wouldn't be quiescent if there was no supermassive black hole feedback. And therefore, quiescence can be used as a proxy, as an indication that supermassive black hole feedback has acted enough to actually quench star formation in galaxies. Is it clear, the idea? So let's talk about the effect of feedback on the gaseous halos around galaxies. I'm going to start with a phenomenon that we call the halo X-ray luminosity dichotomy. So galaxies are surrounded are at the center of the Darmstadt halos. These Darmstadt halos are filled with gas with different fractions at different halo masses, as we're seeing here. This gas is mostly hot, and therefore it emits in the X-ray band. From the simulations, we can actually forward model the output of the simulation into observer space and essentially produce spectra and images in the X-ray wavelength, exactly as they could be seen with Chandra or other X-ray telescopes. We know the gas density, the temperature, the metallicity of the gas, and we can apply plasma models in order to obtain what every parcel of gas in the simulation may emit in X-ray across a certain wavelength. And then we can study these spectra or these images in X-ray. And so we are really going to observer space. According to the illustrious TNG simulations, the emission from the volume filling gas in and around galaxies is different for star forming and quiescent galaxies. This is X-ray luminosity integrated within a given volume around galaxy as a function of galaxy magnitude, in K-band, or stellar mass. As you can see, according to the simulations, blue galaxies are in a completely different scaling relation. But in particular, at this transitional mass regime of Milky Way and Andromeda galaxies, around star-forming galaxies are surrounded by X-ray brighter halos than similarly massive quiescent galaxies. Now, this is a manifestation of the ejective and prevented feedback from supermassive black holes. As I showed you earlier, supermassive black holes in our model removes the gas from the center region of galaxies and the halo, so it's ejective, so brings down the density, but at the same time heats up the gas and possibly pollutes the gas with high metallicity gas from the inner region of galaxies. However, X-ray luminosity depends in different ways on temperature, density, and metallicity, and the winner is the metallicity, so that quiescent galaxies have been removed so much of their gas, of their hot gas, that they are X-ray dimmer. Now, these results are tentatively confirmed by individual observations of a few blue disky galaxies and massive quiescent elliptical galaxies seen with Chandra. This is tentative for a number of reasons, and I'm happy to tell you why. It's difficult because there's also a lot of X-ray sources that are point-like, like AGN and X-ray binaries. But also it was surprising because usually people go after massive elliptical galaxies to see their X-ray luminosity. In fact, this dichotomy between the X-ray luminosity of star-forming and quiescent galaxies is not just predicted by TNG, but also other simulations like EAGLE, and not just within east central regions of galaxy, but also large galactocentric distances. These plots essentially are translating what I just said. And in fact, this is true not only when we integrate the X-ray luminosity in the soft band across a large band, say between 0.3 and 5 keV, but it's also true when we are going to look at the X-ray luminosity from individual metal lines, in the metal line emissions. And for example, if we were able to detect oxygen 8 and iron 17, these are in the soft X-ray band, and could do profiles, simulations like TNG, EAGLE, and SIMBA, they all agree that the properties of the CGM of the circumgalactic mediums are different for star-forming and quiescent galaxies at fixed galaxy stellar mass. And this is very powerful because it's really independent on the underlying details of the black hole feedback implementation. Now, I'm going to skip this, and the question is, but we have other X-ray observations, not just with Chandra or XMM, but with eROSITA. So eROSITA, as you might know, is a German-Russian X-ray telescope. It was launched in July 2019. I've been an external collaborator since the time of my PhD. And the main science goal of eROSITA is actually to constrain dark energy and the functioning of the cosmological model as a whole by observing clusters and groups of galaxies. If eROSITA could finish its All Sky survey that was supposed to last for 4 years, it would be able to see something like 10 to the 5 galaxy clusters. In the meantime, eROSITA has observed to a smaller depth all the sky, and in particular a region in the sky that is also overlapping with the Gamma survey. This is a part of the early data release of eROSITA. It's called EFEDS, eROSITA Final Equatorial Depth Survey. It includes something like 100 square degrees, of which 60, 65 are in common with Gamma. And so we have actually undertaken an experiment and seen whether with the eROSITA data, we can confirm or not this dichotomy between star-forming and quiescent galaxies in the circumgalactic medium. However, with eROSITA and with this exposure, we cannot detect the CGM of individual galaxies, so we have to do stacking. And 2 works that come out in the last year, they're all based on EFEDS data from eROSITA, but different ways of connecting the X-ray photons to underlying galaxies. In one case with Gamma, in the other case with SCSS. And here you're seeing the X-ray luminosity as a function of galaxy stellar mass within certain aperture within the halo of galaxies. And in the one case, the observational data here in data points does not support the diversity of star-forming and quiescent galaxies. In this other analysis, the data points here in eROSITA data points supports the idea that star-forming galaxies at fixed galaxy stellar mass are X-ray brighter than quiescent galaxies. So results are ambiguous. They're inconsistent across 2 different analysis of the data, and there's many differences in the way the data has been analyzed, has been stacked, and it probably all boils down to the consideration and removal in the stacking of signal that may come from more massive objects or from the high density environment around questing galaxies. Anyway, stay tuned because we can address this now with deeper data with eROSITA. Now, all this was across many galaxies and across average, spherically average results. However, simulations like TNG can make predictions also for individual objects and on a very specially resolved manner. And so, for example, as in this way, this is actually our own galaxy. This is what people see when they look towards our own galactic center. You may know the Fermi bubble. So here what you're seeing is in red is the emission in gamma rays and the notable Fermi bubbles, these two cocoons coming up above and below the disk of the Milky Way. And a couple of years ago, with the eROSITA data, people have discovered another cocoon of X-ray in emission that nicely paired the North Pole. This other feature was known since 20 years, and they're now called eROSITA bubbles. And people have gone and studied the properties of the gas in the regions occupied by these bubbles. Gas is outflowing excuse me, I want to put it down. Okay. Gas has been measured to be outflowing with speeds that go anywhere from 300 to 1200 kilometers a second, but the gas is certainly hot, 10 to the 6.4, 10 to the 7 Kelvin, and this is why it emits in X-ray. Now, fundamentally, we have noticed that we have found that our simulation naturally return eROSITA-like bubbles. In fact, in our simulations, we have something in TNG50, we have something like 200 objects that we can call Milky Way and Andromeda-like galaxies. These, you can see them face on and edge on in the stellar-like composite. Now, if we take one galaxy, this is a stellar light, this is disk edge on in stellar light. This is in gas density. If we go and look at the pressure or the X-ray luminosity, we see that TNG50 simulated Milky Ways are surrounded by one or more cocoon on overpressurized gas that emits in X-ray. This is the case for this galaxy, where we can see that, and within that, I am so sorry about this. Maybe I'll pick this up, and sorry about this. Hello. This is Annalisa, but I'm giving a colloquium. Thank you. Thank you. Bye-bye. Thank you. Bye. I apologize. So in our simulation, black hole-driven wind triggered these high-velocity outflows that enrich the gas above and below the galaxies, heats up the gas to supervirial temperature, and shocks the gas in these coherent fronts that are associated to the higher density region that emits in X-ray. This is the case with one galaxy, and in fact, we have it in many galaxies in our simulation, TNG50. In fact, the majority of star-forming galaxies show this kind of phenomena above and below their disks. And these, again, are manifest as overpressurized cocoons of gas, here shown in pressure, of hot gas, as I said, 10 to the 6, but also 10 to the 7 Kelvin is super virial, and they have morphologies that are suggestively similar to the one of the eROSITA bubbles seen in our own Milky Ways. Now, what is strong about our simulation is that we have more than one Milky Way, and we can look at them at different times. So even if we look at our 200 galaxies at the ratio 0, they all come with diverse expansion velocities. Their bubbles come with all the expansion velocities and ages. In fact, they span bubble sizes from a few kiloparsec to 100 kiloparsec, but also bubble expansion velocities from a few hundred kilometers a second to 1,000, 2,000 kilometers a second, essentially actually placing the Milky Way observational constraint well within the ballpark proven by our simulations. And just to give you again, the point is that in our model, Rosetta-like bubbles are inflated by episodic kinetic energy injection from the supermassive black holes. The gas is pushed out of the innermost regions of galaxies. It emerges along the path of least resistance, namely perpendicular to the stellar disks. High velocity outflows develop and often produce supersonic shock fronts that are the ones that manifest themselves as bubbles and shells. Good. Now, I skipped this implication, but the main implication of our paper and the TNG-50 simulation is that it would appear, according to our model, that bubbles similar to the Fermi and Rosetta bubbles may not be a unique phenomenon for the Milky Way. There could be a large number of galaxies, Milky Way mass and Milky Way type, hosting this kind of phenomenon. However, it's unclear whether we can see them any soon. It's going to be very hard to see them with Rosetta because they require a long exposure time, and also the need of distinguishing the signals of the external galaxies from the signal coming from our own galaxies. But this is our claim, and this is what we could go after with future observations. In fact, whether this simulation, this phenomenon may happen on a galaxy by galaxy basis. It can also manifest itself, again, going back to population, at the population level. Beyond individual galaxies, again, our simulations predict that outflows driven by supermassive black hole shape the physical properties of the gaseous halos in an angular dependent manner. These are stacked galaxies from the simulations in density, temperature, and metallicity. And where you can see that, according to our model, supermassive black hole feedback produces lower density, higher temperature, and higher metallicities along the galaxy's minor axis. This is a mass-dependent phenomena that, again, is most strongest at the Milky Way mass scale. Now, this is as a function of halo mass, so the Milky Way is around 10 to the 12 solar masses. But it goes away at the higher mass end. We are making predictions for how this phenomenon could be detected at these masses. And we think that future observations could be able to see this phenomenon even in stacking when studying the X-ray hardness, which is essentially the color in X-ray. Again, this is something we can prove with the Rosetta stacks in the future, but the jury is still out. So, now, moving from the gaseous halos to galaxies, and even though these predictions remain predictions to be validated or invalidated, in the meantime, this manifestation of supermassive black hole feedback into angular modulation of the physical properties of the gas seem to be consistent with observations we have already in hand that relate to galaxies. Not the gas, but galaxies. So with Ignacio Martin Navarro, we have turned to SDSS data, and we have studied the star formation status in SDSS data. And so imagine that we can take a massive galaxy, and a massive galaxy is surrounded by, is immersed in its own dark matter halo. A gaseous halo is surrounded by a smattering of satellites. And suppose that we could see this galaxy either edge on or whatever in a given angle, okay, where we can define an orientation angle with respect to the stellar light. Now, according to SDSS data, the fraction of satellite galaxies that are quenched is lower along the minor axis of their central than along the axis of along the major axis. You can see this here, quiescent fraction of satellites as a function of orientation along their central, where you can see is lower along the minor axis and higher along the major axis. This has been obtained by stacking 120,000 satellites around 30,000 centrals, and could only be seen statistically with this stacking, but is statistically significant, even though it's a small phenomenon. Moreover, and of relevance here is that this phenomenon was predicted by the TNG simulation. And here you can see this angular modulation of the quench fractions of galaxies around centrals in TNG and in SDSS, agreeing at a surprising level. Again, the modulation is small, of the order of the percentage level, but is significant. And moreover, in SDSS, so in real galaxy data, we see that it's stronger for satellites closer to their center, for lower mass satellites, for halos with more massive centrals, and halos with relatively more massive supermassive black holes. Now, thanks to the fact that we have TNG, we can propose an interpretation. And we have this TNG simulation, that we have the counterpart from a previous model, which is called Illustrate, which is the same model but different implementation of supermassive black hole feedback, where there's no modulation. And also, we find with TNG that the modulation is driven by satellites that quench within the Redshift zero host. And so we can conclude that this anisotropic satellite quenching is actually the quintessential manifestation of supermassive black hole feedback driven from the central, affecting the gaseous halo around the center, and which in turn affects the evolution of galaxies. So what happens? Lower density regions in the halos in the halo gas are carved by supermassive black hole feedback, as I've shown you many times in the talk. Lower density means lower run pressure stripping on satellites. Lower run pressure stripping means lower gas removal along the orbit, and therefore relatively less efficient quenching of the satellite. If these supermassive black hole feedback effects on the halo, on the density of the gaseous halo, are angle dependent, then also this effect is overall angle dependent, hence our angular modulation signal. So to conclude, we think that the anisotropic satellite quenching is the manifestation of the far-reaching and non-isotropic effects of supermassive black hole driven outflows that at the level of Milky Way mass scale and a bit below, and that translate what we see in the Milky Way and Milky Way-like galaxies as Rosetta bubble to the statistical galaxy population, as we can see here in the case of one galaxy. This brings me to my conclusions. So I show you that the hot gaseous halos around normal L-star, Milky Way, Andromeda-like galaxies encode quantitative and possibly observable constraints on the quenching of the star formation in galaxy, and therefore on the feedback mechanisms. I've talked about a few phenomena, the X-ray luminosity dichotomy, whereby star-forming galaxies are surrounded by X-ray brighter halos than quiescent galaxies at the Milky Way mass range, that E-Rosetta-like bubbles are plausibly driven by supermassive black hole feedback according to our simulation, and should produce E-Rosetta-like bubble, should be present in a multitude of Milky Way Andromeda-like galaxies. These E-Rosetta-like bubbles in individual objects could be manifest at the population level with an angular modulation of the physical properties of the CGM. And this angular modulation of the CGM is consistent, we think, with a novel phenomenon that is in galaxy data, for which observed satellite galaxies are less frequently quenched along the minor axis of their central rather than along the major axis, and this is because of the effects of supermassive black holes of their central. Many of those are predictions that are consistent across different simulations with disparate different models, and many of these are predictions. Some of them are tentatively supported, but the jury is still out. And this is because it's very hard to actually detect the volume filling hot gas around galaxies. An advertisement, the future, as always, as we say, is bright. It will be possible in the future to do the imaging and to do X-ray IFU, so spectroscopy of the hot volume filling gas in halos. This is the goal of a NASA probe mission concept that my team and I are contributed to. It's called LEM, the Line Emission Mapper. This is a X-ray microcalorimeter that will allow us to really detect the gas and its kinematics thanks to its fantastic angular, spectral resolution in the X-ray bands, and also its large field of view compared to other CCD resolution missions like Chandra so far. And we are predicting that LEM should be able to detect and map the hot CGM in emission out to the Vira radius of halos around Milky Way, like galaxies in the local universe. So stay tuned with this. And if you're interested in our simulations and in playing with the data, as I mentioned, all the data is publicly available and you can find it online at this website. So thank you very much.
Thank you very much, Annalisa.
And sorry again for this phone call. It was an insisting person.
Don't worry. Perfectly in time. Does anyone has any question? You can unmute yourself or write in the chat and I will read the.
How many of you guys work on actual galaxies rather than other topics?
Well, I may have a question meanwhile. We wait for somebody else. Yeah, I'm not an expert in simulation, so maybe or I may have missed it. So you told us that basically massive galaxies are the one that are quiescence, and that the main mechanism for quenching the star formation there is it's a supermassive black hole winds that can remove gas and heat gas and then quench star formation. Yeah. So we also know that in radio loud active galaxies, active galactic nuclei are hosted also mostly in massive galaxies. And we also know from observation that actually the active galaxies, radio loud active galaxies with prominent radio jets have in some cases higher star formation than not in other radio quiescence, let's say. So there should be also some kind of positive feedback in the star formation rate, right? With this AGN outflow that can actually trigger star formation, just compressing dense cloud. So I'm wondering if you have taken this into account or if you see something like that in your simulation.
Yeah, no, thank you very much. Okay, of course, there is a big debate about positive and negative feedback driven by, say, supermassive black holes. And actually, we have indication that we have positive feedback also in our simulations. It's just that it's not at the level, even in, I mean, certainly in satellite massive galaxies where there is compression of gas because of environmental processes, but we're investigating also the possibility that this happens also in the outflows of our massive galaxies themselves. The point is that whether this can happen for a certain galaxies, for a few galaxies, or for a period of time, this still doesn't negate the fact that at the population level and at the end of the day, the galaxies will be quenched. And so actually this idea that there is also positive feedback, a positive effect of feedback of the same quenching mechanism is actually very intriguing. It makes the picture complicated, but may actually accelerate the process, because if you allow the galaxy to have some positive feedback, in a sense, it it accelerates the usage of the gas by doing some star formation, then it may actually reach the quenching state even faster. So we have, the simulations would naturally produce all these phenomena at the same time, but the fact that the population as a whole is quenched at ratio 0 and has to be quenched at the level that is observed is not a priori in contradiction with the possibility that in some instances, for some period of time, in some galaxies, there can actually be positive feedback. Yeah.
Okay, thanks. Perfect. Thank you very much. So any other question?
Hi, Annalisa. Great talk. And not a real expert in galaxies, but I have a more technical question.
Mm-hmm.
So in Illustris TNG, so maybe you already mentioned that, but what kind of types of particles do you actually have? Like, is that stars, I guess, and then some dark matter particles, and what else is there?
So we have dark matter particles, and these are, say, different simulations, could be 10 to the 4, 10 to the 5, 10 to the 6 solar masses. Then there are stellar particles. They represent population of stars with a given IMF, an initial mass function, and then they are allowed to evolve. And these, again, depending on the resolution of the simulation, they may represent population of 10 to the 4, 10 to the 5, even 10 to the 7 solar masses of mono-age populations. We have supermassive black holes. These are also particles. So dark matter stars and black holes, they're all Lagrangian elements. Black holes, as I mentioned, we don't know how they form. When halos go beyond a certain mass, we give a black hole with a certain mass at the beginning, between 10 to the 6 and 10 to the 5 and 10 to the 6, and then it can grow. And all of these, they all interact gravitationally, right? Dark matter stars and gas, and all with each other. But there's also gas. And the gas also interact gravitationally with all of them, but the hydrodynamics is solved in our code in a pseudo-Lagrangian fashion. So gas is represented as cells, but as I shall maybe here, let's see if we can go there. The cells in AREPO, which is the code we use, are not Cartesian, but they are. So we do a so-called Voronoi tessellation of the space, and as you can see them there. So the cells are tetrahedrons, and this is just a slice, so it's a cut through the cells, and the cells are not cubes, they are different shapes, and they can change the shape, and they can change the size, depending on what type of physical phenomenon the cells are supposed to mimic for. And so, for example, in our code, which is called a moving mesh, the cells are also move with the Bach motion of the gas flow, and the cells have fixed mass, represent fixed mass, and so at better and better density, they are smaller and smaller. Yeah, and so
I see. But so particles can they change from one type to another? Mm-hmm. Like
this is what we say star formation. So gas cells can be converted into stellar particles. If so, the star formation for us is a recipe. Nobody knows how star formation works. We'll always be subgrid at some level, but in our models, it's very simplistic. We just say if gas exceeds a certain threshold, it can make star formation. We do it stochastically. So based on the physical properties of the gas, we expect a certain level of star formation rates, and then we convert portions of entire gas cells into stellar particles. Yeah, but stellar particles don't die. So stellar particles are always there. They are age. They lose mass because they represent population of stars that they evolve with time, that they do feedback, they evolve, produce metals, etc. Yeah.
Fantastic. Yeah. Thank you very much. And so the supermassive. So what? So for the supermassive black holes, how? I mean, what qualifies as a supermassive black hole? I mean.
So indeed, so these are different type of particles in the sense that they are again, we treat them as Lagrangian elements, but they are particles that start with a mass, as a seed mass of 10 to the 5, 10 to the 6 solar masses. We place them by hand in halos, at the center of halos, when halos go beyond, say, total halo mass of 10 to the 10 solar masses. So this usually happens very much earlier in time. And then,
so you use some type, sorry to interrupt you. So you use some type of luminosity mass function to mass relation to
not
place
even,
them, or-
not even. Any halo above a certain mass gets a black hole.
But what I mean,
then,
how do
yeah.
you decide the mass of the black hole that
The
goes?
seed mass, okay, so this, it gets a black hole with a certain initial mass, say 10 to the 5, 10 to the 6 solar masses.
Okay, so
Then
okay.
the black hole can do something else. It's a special particle. It's called a sink particle because it can actually grow in mass. And how does it grow in mass? By so gas cells can also transform in other ways. Gas cells can give mass to the black holes in the center of the galaxies.
I see.
And
Okay.
the black holes can grow by both gas accretion, and we assume a Bondi formula for the gas accretion. But the black holes can also merge with other black holes. And so as halos merge and galaxies merge, also black holes merge. And so they can grow both via black hole mergers or by gas accretion. Yeah. And therefore, so from a 10 to the 5, 10 to the 6 solar mass seed, black holes can grow up to 10 to the 9, 10 to the 9.5 solar mass halos, black holes, solar masses. And the resulting Magorian relation, black hole mass versus galaxy solar mass, is the result of our simulation. It's a combination of how we do the seeding, how we do the growth, and how we do the feedback. Yeah. Yes.
Thank you.
Sure.
Yeah, very impressive simulation.
Yeah. I have someone knocking at my door. I'll be back in a sec. I'm giving a colloquium mangiando in silence. Sì. Okay, it's not, doesn't ever happen like this. I'm never so wanted.
Okay, so unless anyone else is raising the hand or unmuting himself, I think we can now then. Thanks, Annalisa, again for the very nice talk. Thank you very much for
Guys, thank you very much, and again, thank you for the patience. And it was very nice to see you, Carolina and John, and to meet you all, although online only. Yeah, good. We'll be in touch.
We'll be in touch. Yes. Thank you. Thank you again. Bye, everyone.
Bye, guys. Ciao.